Welcome back, students. In the last lectures, we looked at how we can determine the probability of measuring a specific configuration, specifically with molecular systems in mind using the Boltzmann distribution. Now that we know how to do that, we will try to describe what is happening not to a particular molecule, but to a group of molecules or an ensemble of molecules. So today we will talk about the molecular partition function. And this is the function that we're going to use to describe what's happening to an individual molecule. And then we can in turn see how to apply that to a whole unit, a whole bunch of different molecules. The learning goals for today are going to be to first define the canonical partition function. So when we use a capital Q here, we're going to be talking about a large assembly of molecules, and a lowercase q for our partition function is going to talk about an individual molecule. And we'll see that these two things are related. So we can figure out the partition function, the way the energy is distributed for a large number of molecules, is based off of just one molecule. And we'll see at the end how we can describe the lowercase q. And it turns out it's a product of all of the different degrees of freedom, so translational, rotational, vibrational, and electronic. So we saw in the last lecture that if we have a system, that system is only going to be at one distribution, the dominant distribution or the Boltzmann distribution. This is the distribution that has the largest weight, and so it is the one that the system will relax to at equilibrium. And since its weight is so much larger than any other configuration, it'll only be at that one position. So we can say this, and this is all well and good, but we cannot reasonably expect a system to stay in a single microstate. So we could have a microstate where energy is distributed in a certain way, and we would expect that at some time one particle would maybe lose energy, give it to another particle, and a lot of these different microstates would have the same configuration, but some of them might have slightly different configurations that are all very similar to the Boltzmann distribution. We'll start with a definition of what we mean by ensemble. An ensemble is simply a large collection of identical units or replicas of a system. So we can think of dividing up a swimming pool into 1 liter cubes of water, and those 1 liter cubes are our components to our ensemble, and the entire ensemble is the swimming pool. We'll define a statistical mechanics postulate here. This seems pretty obvious to us, but the average value for a property of the ensemble corresponds to the time average value of the corresponding macroscopic property of the system. So what that means is if I measure the temperature of my swimming pool, I get an average temperature over time of what the swimming pool is, and that average temperature of the entire pool is also the average temperature for my individual units of water. This makes sense to us. We'll then go on to define specific types of ensembles, and for us, our ensemble will be called the canonical ensemble. The canonical ensemble is just, again, a specific type of ensemble where each unit has the same volume, temperature, and number of particles. There's other types of ensembles. For example, there's a microcanonical ensemble where they have the same volume, number of molecules, and energy, slightly different than temperature. We can figure out the energy of the whole ensemble, which is this EC for the energy of the canonical ensemble. It is simply the sum of all of the different energies that are possible for each of our units. And then if we have some degeneracy, we have an occupation number here. So if we have our 5-unit system as shown here, if we have a 1, a 2, a 3, but then maybe a 4 and a 5 are the same, we would have 1, 1, 1, and then 2, and we add all those up and figure out the total energy of our system. What we can do then is calculate the weight of an ensemble to have a specific configuration. And this is the exact same thing that we've done before. So the weight of the canonical ensemble is NC, the total number of units for our ensemble, and then we divide them by the occupation numbers of each possible energy level. So this is, again, the exact same thing that we've done before when considering individual energy levels for molecules. With this, we can then define a probability of observing a certain energy level. And again, the exact same as you've done before. Here we have our E raised to the negative beta times the energy of the certain level. Here, the weight of this particular configuration is serving as a degeneracy term. And then we can divide by Q, where Q is the sum of all of these E to the minus beta times the energy terms here. Now, what does this probability look like? We've already seen that as the energy increases, the weight increases. So as E gets larger, the weight of that distribution will get larger. However, as E gets larger, E to the minus beta E will get smaller. So what we have are two opposing functions that we're multiplying together. And our Q here, this is a constant, it's simply a normalization factor. So what happens as we multiply the weight with increasing energy against E to the minus beta EI, in this case we have over Q, that's decreasing, we end up having the product of these two functions, which represents itself like this. And we can see that the majority of components to our ensemble will have energies at the average energy or very near the average energy. If the number of units is large, so 1 liter chunks of a swimming pool, it's a pretty large number that we'd get, this distribution will be very narrow. And we're expect that almost all of the individual components to our ensemble have very near the average energy. Again, thinking about the pool, if we measure one end of the pool at 20 degrees Celsius, we're not worried to jump into the other end of the pool and expecting that it might be either freezing cold or boiling hot. It's probably going to be within a few degrees of 20 degrees Celsius if one part of the pool is. Now, what can we do with this? So how can we describe this capital Q, which is the partition function for our ensemble? We call this the canonical partition function. We can see here it's simply the sum of all of the individual energies of the individual components of the ensemble raised and multiplied by beta and then raised the E raised to that. So let's consider a simple system, not a large swimming pool, but a simple system in which we have only 2 units. And again, I'm showing all this math here. We'll go through it one step at a time. So the Q is simply the sum of E raised to the minus beta times the energy levels of our 2 component system here. And so this is going to be the energy of part A, and we have maybe a whole bunch of energy levels that could be for part A, and then energy for B, and a whole bunch of different levels that could be for part B there. So what we can do is actually carry out this sum. And what we get when we carry out this sum is the following. So the sum of E to the minus beta times epsilon AN plus epsilon BN, if we're summing over all the n's, we have to do them individually. So we have one term that's going to be epsilon A0 plus epsilon B0, and then we'll have epsilon A1 and epsilon B1, and go all the way through up until Bn. And then we also have epsilon A1 and B0, and then we have A1 and B1 and A1 and B2, and then going all the way up to Bn. And then we do the same thing for A2 and A3 and all the way up to An. We can use the exponential properties to pull these things apart. So here we'll have, in this term, we can say epsilon or E to the negative beta epsilon A naught times E to the negative epsilon B naught. And then we do the same thing for all of our other terms. When we do this, this allows us to actually factor them apart. So we can factor out this sum into E to the minus beta epsilon A naught plus A1 plus A2 and so on all the way up to An, and then times B naught and plus B1, B2 all the way up to Bn. And if we multiply these things together, we would end up back with this term here. Now, what do we have? Well, this is simply the sum of E to the negative beta epsilon A n, going all the way from n equals 0 to whatever the largest number of n is. That's simply the partition function just for unit A. And this is simply the partition function for unit B. And so in this case, for our 2-component system, we have discovered that Q, the partition function of the ensemble, is simply equal to the product of the partition functions for the individual units here. And in this case, since we have two units, our capital Q is equal to lowercase q squared. This is true in general. So if we have a system of distinguishable units, capital Q is always equal to lowercase q raised to the n, where n is the number of components of the system. In general, we don't have distinguishable units. So if we're going to apply this to molecular systems, we can't tell molecule A apart from molecule B, and we have to do a correction for that, and it's the same correction we've seen before. So if we have indistinguishable units, our partition function is q to the n, and then divided by n factorial, which will correct for overcounting we get when we try to distinguish the units that we actually can't distinguish. So why is this important? Well, how do we define our canonical ensemble? We can go back a couple slides here. And we define the canonical ensemble as each element having the same volume, temperature, and number of molecules. There's no set definition for what the volume, temperature, and number of molecules can be. And so it turns out that we can define our canonical ensemble as consisting, or the units of our ensemble, as consisting of a single molecule. So our canonical ensemble can be made up of identical units with the same volume, temperature, and number of molecules, and that number of molecules can be 1. So what this gets us then is a system in which each Q here is corresponding to the partition function, not for unit A, but for molecule A or molecule B. This capital Q reflects the energy sort of the whole ensemble, and it's dependent on the partition function for the individual molecules of that ensemble. So we'll see in the next couple of lectures that we can relate this capital Q to many system properties, such as internal energy, heat capacity, entropy, and so on. And this capital Q is related to this lowercase q. And in the next lecture, we'll relate this lowercase q to the energy spacings of different degrees of freedom. So we have quantized energy levels, which gives us Q, or lowercase q, for our molecules, which in turn gives us the capital Q for the whole ensemble, which then determines the ensemble properties, such as internal energy, heat capacity, and so forth. So this is ultimately where we're going to be going and trying to build up our bulk properties that we've been describing since the beginning of class based on the energy levels of our different components. Based on quantum mechanics. So before we end for today, we can look at how Q depends on the molecular energy. The total energy of a molecule is simply the sum of all of the individual energy levels. So here, T is for translation, R rotation, V vibration, and E electronic. So if we want to figure out the total partition function for our molecule, Q tot, that's equal to the sum of the degeneracy of the molecular degrees of freedom, and then times E raised to the minus beta E total. What this is we can pull this apart. So the degeneracy is simply the product of the degeneracies of every single level. And then we know that the total energy is this sum up here. So we can say that this is equal to the sum of all the different degeneracies for all of the different degrees of freedom times E to the minus beta, now with the sum of all of the energy levels. With this, we can use exponential properties, pull it apart, and get that Q total is equal to the sum of our translational degeneracy times our translational energy levels, and then the rotational, vibrational, and electronic. Now, what are these? Well, the sum of our E to the minus beta times our translational energy levels is simply the translational partition function. And this is the rotational partition function, the vibrational partition function, the electronic partition function. So what we can see is that we can figure out the total molecular partition function simply by identifying the partition functions for each degree of freedom that the molecule can have, translational, rotational, vibrational, and electronic, and multiplying them together. Then we can go back once we know the total microscopic partition function and figure out the partition function for the ensemble, and then use that to get the system properties. And this is what we'll be doing in the next couple of lectures. So in the next lecture here, what we're going to be doing is investigating each of these partition functions and figuring out how the degrees of freedom, the energy level spacings for translation, rotation, vibration, and electronic excitation actually create very different partition functions. We'll get mathematical expressions for all of these and be able to figure out the total partition function for molecules. And then in the section after that, we'll use that to figure out the bulk properties of the system.